Hello, this is Ron Wade, Principal Systems Engineer with Renaissance Electronics in the Timing Division, and I'm back with part 3 in our reference clock, PCIe reference clock jitter series, and we're going to talk about common clock architectures today. So the basics of a PCI Express interface, there's the link, and the link is composed of lanes. The smallest link, therefore, is one full duplex lane, which is shown here where we have a by one on the root complex or the host main board, where we have a receiver channel and a transmitter channel. And then on the endpoint plug-in, we have a transmitter over here and a receiver channel as well. And the data flow is shown by the gray arrows. So this looks a little bit like 1, 2, 3, 4 PLLs per lane, 1, 2, 3, 4 reference clock requirements. But once we get into the common clock, we'll see some great simplifications. So the definition of common clock is that the reference clock for the transmitter and the reference clock for the receiver are both sourced from a single ref clock. And a single ref clock source means that the transmitter PLL and the receiver PLL are driven by the same ref clock PLL with no intermediate PLLs. So we'll delve into that a little bit further in the next slides. So if we take this by one interface and we expand it to a by four, we can see that it starts to look rather complex from a clocking perspective, where we still got the red box around each of the receiver transmitter pairs that clocks, and we have the gray arrows showing the data flow. So each pair of arrows is a by one lane, and here we have 4 lanes making the link. So there appear to be a lot of PLLs, a lot of clock requirements. However, the PCIe common clock definition leads to a very simplified interface. So here we go back to the by one lane, and we see that if we declare a common clock for both for the entire system, here we show it with a ref clock in the middle, and then over here, because the clocks are common, we can combine the transmitter and the receiver PLLs into a single PLL. Because remember, the frequency information here is common because it's coming from one place, the reference clock. So the frequency information over here will be the same as the frequency information over here. And all we have to do on the receiver then is deal with the phase of the data channel coming in and recover that phase to sample the data properly. So if we take this and expand it to 4 lanes, we get a by 4 that looks like this, where we have all of the receivers in the host up here, the transmitters here, and yet we have a single TX-RX PLL with the ref clock in the middle and another one over here, TX-RX PLL on the endpoint. And you can see that we've expanded to a by 4, and we still have a single PLL that's needed in each side of the interface. So a great simplification in the implementation also for common clocked architectures. So another way of looking at this is that all lanes in a common clocked PCIe link share the same clocking. So the other thing to note is that because everything's coming from this one ref clock source, or this one ref clock generator, the PPM difference between the host and the endpoint is 0. Hence, being able to share the frequency information. Examples of common clocked architectures are shown on this slide, and recall the definition: a single ref clock source means that there are no PLLs between the transmitter and the receiver. So here we have a single ref clock generator that's driving both devices. Here the SoC has got the ref clock generator internally, and it's driving the transmitter, and then there's an output from the SoC, an external clock output to drive the receiver. This is still common clocked. Down here we have a ref clock and a driving the transmitter, driving a fan-out buffer, driving the receiver. And this is still common clocked because if we go back this way, we don't encounter any PLLs until we get back to the source clock, the reference clock. And even if that ref clock generator is inside the SoC, again, you can add a fan-out buffer outside and still be common clocked. So let's look at some more complicated possibilities here. Here we go back to our system where we have our root complex and our PCIe switches. And if we were to try to brute force this, we would have a reference clock generator. And again, that could be inside one of the SoCs, but I'm showing it discretely here for ease of drawing. And we would have a fan-out buffer for this segment, a fan-out buffer down here, probably a larger number of outputs, and then a fan-out buffer fed by this fan-out buffer to get to these devices down here. So that's kind of hard to do in a large system. You've got a lot of clocks to run. The distances become prohibitive, and it's kind of complicated. However, what you can do with PCI switches, some switches, and you should look at your switch vendor, is you can break this big PCI interface into these segments, and then each segment can be clocked in a common clocked manner. In other words, the transmitter receivers up here are all clocked from the same source. And then the switch has the ability to allow a different domain. And then down here, you would have a common reference clock source so that these interfaces would be common clocked, and likewise over here and then down here as well. So that is one of the great benefits of PCI Express switches. You can actually take this really complicated PCI interface and segment it into common clock pieces the pieces are much smaller than the overall system. Okay, that's it for now. The next presentation in this series will be on independent reference clocked architectures, and I want to thank you for watching.